happy to introduce our speaker, Dr. Yuanzhi Li. Yuanzhi is a assistant professor of machine learning at Carnegie Mellon University. At the same time, he's an affiliate faculty with us. And he has done very interesting work in deep learning theory and natural language processing. And so today, he's going to present something on how to understand the mixture of expert layer in deep learning. Let me add one sentence here. So Yuanzhi is our affiliate faculty, and he would like to work with our students. If you are interested in deep learning theory, right, and the problem at the intersection of NLP and deep learning theory, please just reach out to him. Okay, thank you. Yuanzhi, whenever you're ready, please start.
Okay, thank you. Yeah, thank you very much for the invitation, and thank you very much for the introduction. Yeah, sorry. So today I'm going to talk about the mixture of expert layer in deep learning. Okay, so as usual, my talk will be extremely simple, and you can feel free to interrupt me at any moment if you have questions. And I prefer to be interactive. So if you have questions, please don't hesitate to ask. Okay, so this is a joint work with a bunch of excellent students, also Quan, professor at UCLA. Okay, and what's the motivation of this talk? Well, the motivation of the talk is the so-called foundational models. Okay, so foundational models is a special type of model where we want the model to do a lot of things together. Okay, we don't want the model to be just specialized on one particular job, but we want the model to be as general as possible. So at the beginning of the foundational models are something like an image model that are trained on ImageNet, and those models are found to be able to recognize general images. And after that, people have developed foundational models for languages, such as you may heard of GPT-3. It's just a language model that can understand all kinds of languages and do all kinds of things on the languages. Okay. So of course, people want the foundational model because foundational models are somehow the first step towards maybe artificial general intelligence. Okay, so this is a model that everybody cares about. And how do you get a foundational model? Well, the foundational model typically are obtained using the following way. So you just create a data set that are as large as possible. And then you use a gigantic network, and then you train the network. Okay, you get the foundational model, and then you can apply the foundational model into different downstream tasks. Okay. And the key of the foundational model is that this model is very, very general. Okay, it's capable of doing a lot of different things on downstream tasks. Okay, and that definitely requires a large amount of data, and it also requires a very, very large model. Okay, so at the beginning, the foundational models were mainly designed on the image side. So you just train a neural network on like a general ImageNet data set or data set that contains a lot of different images. And then the network is able to recognize general images, not only images from that data set, but also other images. Okay, for example, you can recognize real world images. Okay, so those models are extremely useful. And the foundational model for image recognitions are of size in the order of 100 million. Okay. But after that, move to the language world. Well, the foundational model now becomes exponentially bigger. Okay, so a GPT-3, which is a foundational model for languages, is like 1,000 times bigger than a foundational model in images. Okay, so GPT-3 is just a general model that can do a lot of different tasks on languages at the moment. Okay. And after designing the GPT-3, which is a foundational model for languages, people were not really satisfied with this scale. Okay, so Google, a bunch of researchers at Google really went banana here, and they make the model even 10 times bigger than a GPT-3, okay, which is 10,000 times larger than a vision, standard vision model. Okay, so they create this model called GLAM. And this model has 1.2 trillion parameters. Okay. And the question is, how is the model of that size being able to train, and how do we even use a model of that size? Okay, so just for reference, GPT-3, I mean, a standard VGG requires 1 GPU. Okay, but GPT-3 is 1,000 times larger, so it requires 1,000 GPU to train couple months. And even to inference a single sentence, GPT-3 already requires a lot of computation resource. So how can we continue this trend and get models that are even 10 times larger, or maybe next couple of decades, we want a model that are 1,000 times larger than GPT-3 as our foundational model. Okay, so how do we even do something like that? Are we going to just collect maybe 1 million GPU and just use all those resources, or are we going to do something clever? Okay, so it turns out that the Google people did something clever when they trained this foundational model, and they used a newly invented layer, which is called the mixture of expert layer in this foundational model. Okay, and the mixture of expert layer ensures that although this original model is 1.2 trillion large, but during one inference time for one particular data, only 95 billion parameter in this model is really active. Okay, this means that only 1/100 fraction of the model is actually active to solve one particular instance. Of course, these active parameters are changing if you use different instances. Okay, for example, if you parse one particular sentence, then maybe like the left part of the model is active, and if you parse another sentence, maybe the right part of the model is active. Okay, so this is called, I mean, this particular network architecture is called mixture of expert. Okay, and mixture of expert is really, really important in nowadays, in deep learning nowadays, because we really want to scale up the model. Okay, we are not really satisfied with 1.2 trillion. Maybe we want 10 trillion, or we want 100 trillion. And right now, given the computation resources, the only way to train a model of that large is to use the so-called mixture of expert layer. Okay, so mixture of expert layer is going to increase the capacity of the model and reduce the training cost, and also improve the inference speed. Okay, so it's kind of getting the best of everything that we have, that we are wanted. Okay, any questions? Okay, cool. So what is a mixture of expert layer in deep learning? Okay, a mixture of expert layer looks like this. Okay, so this layer contains two parts. The first part is the expert part. Okay, typically there are maybe 10 to 100 experts. Okay, so each, I mean, mixture of expert is one particular layer. Okay, so this is one layer in your neural network, and you can connect those MOE layers. Okay, and one particular mixture of expert layer consists of two parts, the expert part and also the router part. Okay, so what does this network do? Well, it just has, let's say M equal to 100. So you have 1, 2, 3, up to 100 many experts. All those experts have the same architecture. Maybe they're just one hidden layer fully connected neural network. And then you have this router network that decides for one particular input which expert you are going to use. Okay, for example, on an input saying I'm very happy, you may process that sentence with expert 1, and on input maybe I am very sad, you will process that sentence with expert 2. And also it may just be like token level gating. Okay, so maybe I will process the word I with expert 1, and then word am with expert 2, and word very with expert 3, and word happy with expert 100. Okay, so just use this router to decide which part of the network will be active on this instance. And you already see that the inference time or the activation of the entire network only depends on the size of one particular expert. Okay, although it's going to have 1,000 or 100 experts like this model, okay, just for one particular instance, only one of these experts is going to active. Okay, so only 1/100 fraction of the network parameter will be active. So it's going to be very, very efficient, both in terms of training and in terms of inference. Okay, any questions? Okay, cool. So the router network will decide which expert to use on this particular input. Okay. And since the, mixture of expert itself is not really a very new concept, okay, it turns out that actually the mixture of expert model traces very, very deep back in theory or in machine learning, even 30 years ago. Okay, so people were thinking those experts models, those are actually the first generation of machine learning models. Okay, people were using very, very simple model like decision trees, but then they use different decision trees as different experts. Okay, and then they want to mix them together. Okay. And the mixture of expert model is reinvented in deep learning back to 2013. And now they are actually used very heavily in foundational models. Okay. And it's actually expected that the next generation of foundational models are all mixture of expert based. Okay. So you cannot really do foundational models nowadays without a mixture of expert because they are just so big. And it's impossible that you train the model without an MOE layer. Okay? So big places such as Google or other companies, okay, their foundational models are now all mitigated to mixture of experts. Okay, so we have to understand this layer in order to be well prepared for the next generation of model in deep learning. Okay, so transformer back in 2017, that's like a big breakthrough in deep learning. And now mixture of expert layers are perhaps the second big improvement in deep learning. Okay, so the new generation of machine learning models are all going to be mixture of expert like. Okay, any questions? Okay, cool. So we want to understand the mixture of expert model better so we can be better prepared for the future. And that's kind of the role of our researcher as a theoretician. Okay, we want to help people to understand what's a mixture of expert model doing and what's the advantage of a mixture of expert model. Okay, so you can just have a better intuition, or maybe you're going to design better practical mixture of expert models, as we will see that there are still several challenges. Okay. So what's the motivation of mixture of expert model? Well, the motivation of mixture of expert is really the API. Okay. So one way of thinking about those experts are that they are just simple APIs that are very specialized and very, very small. Okay. So think about a human brain. Our brain has a lot of different variety of functionalities. Okay, there are some part of our brain that are only specialized of calculation, some part of the brain that are specialized in emotion, some part of the brain are specialized in speech, some part of the brain are specialized in maybe coding or something like that. Okay, so we really want our new generation of foundational models to like our brain. Okay, so this is like a picture of a general compute. But to achieve a general compute or general artificial intelligence, we are not going to train a model that mix everything together. Okay, we want to make sure that the model has a lot of different units, such as a computing unit, a sound unit, a graphical processing unit, a bunch of different units. Okay, and we want those units to work together in order to achieve the foundational model. Okay, and the point is, for a particular input example, I don't really need to call all the units, right? For example, if the input example is just predicting the sentiments, then I just need to call my emotional API. Okay, and if the input example is about calculation, then I just need to call my calculator API. Okay, and the motivation of MOE is really just to think of each expert as an API. And then for a very particular input example, we just call some small fraction of those APIs. Okay, so those are much more efficient compared to a general like transformer or a general convolution nets that are mixing everything together. Okay, we want the model to be diverged and to be specialized in a lot of different APIs. Okay, any questions? Okay, cool. And of course, this is just a motivation. And the motivation is typically very promising. But the question is, would the mixture of expert layer actually work in deep learning? Okay, so we implement the mixture of expert layer, which I will discuss about how to implement them in later slides. But would this thing actually work in deep learning? Okay, so let's just try to work through a very, very simple example of mixture of expert. Okay, so this is some simple example that we did in our group. Okay, so let's just consider the following synthetic data set. Okay, so synthetic data set look like this. This is natural language data set. Okay, so you're going to say, you're going to define some variable names. Okay, those A1, A2, A3, they are going to be replaced by some actual variable names. And then those stars are going to be replaced by the values. Okay, so for example, you can say this sentence. Okay, so this sentence is actually given by natural languages. Okay, so you just assign some value to the number, and then you ask what's the addition or what's the multiplication of some subset of the value. Okay, so if you're familiar with natural language processing, this is actually a very, very difficult task for a standard transformer. Okay, because multiplication is a very difficult task for transformer to learn. Okay, and now to illustrate the power of mixture of expert, let's just consider to artificially create two experts that are calculators. So one of the experts is only going to specialize on addition, and one of the experts is only going to specialize on multiplication. Okay, so what the expert do is, for example, the expert just look at the previous appearance of the two numbers, and then you just multiply them together or add them together. Okay, so they have no natural language processing units. For example, they don't understand what W and Z and X mean, and they don't understand what's the two numbers that you want to multiply. Okay, the expert are very, very naive. They just parse the sentence and look at the previous appearance of the two numbers, such as in this case is, it's this guy and this guy. Okay, and then the addition expert will just, addition expert will add these two numbers, and you will see that the first digit is 9, it's already output, and the second digit is 8. So it will output 8 and then output 8. Okay, so we artificially create these two experts. They are just APIs that the model can call. Okay, and now we are going to train two types of neural networks. The first one is a standard transformer. Okay, and the second one is a transformer with a mixture of experts. So it has these two calculators as their experts. Okay, any questions?
Are the experts trainable during training?
Sorry, what? Can you repeat?
Are the experts trainable, as in will you be training the parameters of the experts, or?
No, the experts are not trainable. They just prescribed two. There are two prescribed experts. The first one just does addition on the last two numbers that is seen. And the second one just does multiplication on the last two numbers that is seen.
Right. Okay. Thank you.
Yeah, so it only has one function. Each expert only have one function and it's not trainable. Okay. And then we are going to, integrate those experts into the transformer network, and the transformer can choose to call the standard natural language unit, or it can call the expert unit to do the computation. And it just cannot really always call experts, because experts only look at the past two numbers. But here I'm asking maybe W times X. Okay, and W times X is not really the past two numbers, so the expert will not get it correct. Okay. And the point is, without expert, okay, without this mixture of expert or without the help of expert, the standard transformer model really sucks at this task. Okay, just cannot learn this problem with millions of training examples because multiplication is super hard. But if we actually equip the transformer with an expert, okay, with these two experts, then just after 5,000 training examples, the transformer is going to solve this problem. Okay, and just look at what it does. So first of all, the transformer knows nothing. Okay, it doesn't really copy the two numbers correctly. Okay, just knows nothing. And after a while of training, it starts to try to copy the numbers, but it's not really doing perfect copying. And then it kind of copy the number correctly now. Okay, but after it copied the number correctly, it does not know how to call the expert. Okay, doesn't really know how to call the expert. This is a false value. You can see 7 times 1 is definitely not 0. So it's not really calling the expert, it's just making something up. Okay, but after that, after the model learns how to copy the correct number with this, natural language processing unit, then it learns how to use the expert. Okay, so you can see mixture of our expert really helps here. If we can hope that the expert specialize on something, for example, multiplication or addition, and then it really helps the model a lot. Okay, so the model learns, first of all, uses natural language processing unit, which is already in this model, to copy those numbers according to this thing. And then it learns how to call the expert. Okay, that's much simpler compared to learning this multiplication from scratch. Okay, any questions?
So, Yunshi, in the case of the expert, is the expert adding or multiplying individual digits or an arbitrary sequence, arbitrarily long numbers?
It's actually adding or multiplying the entire number. So it just separates the number. It just parse the string and then just parse the number part in the string, but it's an entire number. So it separates according to the non-number symbol.
So in the example that you have, if the sequence is 100, 433, 5559, if the addition expert outputs an 8, what operation was actually being performed?
So we actually want to add this number and this number. So yeah, I'm actually being a little bit vague. So it will ignore this last number and just add the previous appearance of the two numbers.
I see.
And then it just try to match the pattern here. So it sees that it should output 988, and there's already a 9, so it output 8 and 8. But if it sees a 10 here, then it will just output end of text because it cannot complete it.
Got it. Thank you.
Yeah. So of course, this is just a simple example that experts are handcrafted. And in reality, we want to train those experts. But just to demonstrate, with a handcrafted expert, at least the router part works, and the model definitely knows how to call those experts. Any questions? Okay, cool. So basically, this is the motivational mixture of expert, and we already see that with an expert, the model is actually much more powerful. Okay, but the key challenge is, in deep learning, those experts, first of all, they are not prescribed. Okay, and second of all, they are not really specialized or different at the beginning. Okay, all those experts are actually have the same structure, and they are just start from random initialization. Okay, and they are trained using the same optimization algorithm with the same configuration. Okay, those experts, first of all, they are not different, and also they are not really specialized at the beginning. Okay, there's no like additional multiplication prescribed experts. So we know that if the experts are prescribed, then it's working very well. But in deep learning, those experts are not really prescribed. And what's even worse, those experts are actually the same architecture. And they are using the same initialization scheme and the same training algorithm and the same training configuration. Okay, so why would we expect those experts to be specialized? Okay, so why would we expect some expert learn addition, some expert learn multiplication, and some expert learn sentimental prediction, and some expert learn like maybe I mean, maybe learn some counting or string copying. Hey, why would we expect those experts to diverge? Okay. So basically, that's the first objective of our research, which is we just try to understand how would the experts in the mixture of expert layer, they actually diversify into the specialized experts instead of just collapsing to a single model. Okay. For example, if you just have, because all the experts have the same architecture, so in principle, it could be the case that after training, all the experts are just going to collapse to a single expert, then this mixture of expert model is completely useless. Okay? It's just a single model, but you repeat it 100 times. And this is just such a waste of resource, right? I mean, after training mixture of expert model, we recover a single model, which is 100 times smaller. And it's such a waste of computation resource. So that's something we definitely want to avoid when training mixture of expert model. Okay, and just in this very simple example, we avoid it because the experts are already prescribed to be one addition expert and one multiplication expert. But when you train the expert from scratch, how would those experts really specialize? Okay, so why won't they collapse to be the same? Because they have the same architecture, they have the same training algorithm, okay? They have the same training configuration. It's not like I train one expert and then I train the other expert, or I train one expert with much bigger learning rate and I train the other expert with much smaller learning rate. And it's not like one expert is a convolution net, the other expert is fully connected. All the experts are actually the same. Okay, so how do they diverge? Okay, and also how do the router dispatch the data to the right expert? Well, we kind of see a demonstration of question 2 in our simple example. So the real difficulty is like question 1, to understand how this mixture of expert layer work. Okay, so our goal as a theoretician, we want to provide some explainable reasoning for how those experts diverge and why they work. Okay, any questions?
So Yunji, from
Yes.
what I understood so far, the advantage of having experts in the way you explained it first, with, for example, the addition expert and the multiplication expert, is that these experts are performing operations that would require essentially an exponential amount of data to learn, but we can hand code it and it's very convenient, right? Whereas
yeah, that's my illustration. The point is, in practice, those experts are not really specialized, so they are just neural network trained from scratch. And we want those experts to be specialized. And for example, if you want a general intelligence, it may be very difficult to train. Like, why is this task difficult? Because it has natural language processing part, and it also have the kind of the multiplication part. Actually, if you only train on multiplication, it's not that hard. But combining with natural language, you kind of confuse the model, and the model kind of try to solve both tasks at the same time, and it becomes very hard. Yeah.
So the key difference here is that instead of having a weighted combination, you are switching between experts, and so it's the switching that's the key aspect, is it?
Yes, exactly. So each expert specializes on one particular thing. For example, this one specializes on copying the digits, and this one specializes on addition. And on one part of the input, you need to copy the digits, and on the other part, you need to do addition. So if you mix them together, it's like an addition and copying operation, which is very, very complicated. But if your expert can specialize, then it's actually solving a much simpler task. Yeah, and that's the kind of the hope that the mixture of expert layer can achieve. And of course, the question is, why would it achieve that? Because the experts are actually just, in deep learning, those experts have the same architecture and they are initialized in the same way. So we really kind of want to understand how they actually evolve and diverge at the end of training. So that's basically the difficulty we want to handle. Does it answer your question?
Yeah.
Okay, cool. Any other questions?
Oh, actually, I have one, Renji. So according to your explanation, do you think we should call them experts or modules? Because usually, right, in the traditional way, or usually the experts actually can do the same task, but they are good at different things, and you want to mix them. And right now, according to your understanding, basically experts are something like modules, and you try to find a way to combine different modules to accomplish the task. So, well, what's your view on that?
Yes, so I think mixture of experts is just a traditional notation borrowing from this very, very early age of machine learning. And at that time, those experts are trying to do the same thing. It's just like a bunch of experts, for example, predicting stock price, and you want to identify the best one. So people just borrow that concept. And I think the best way, as you said, is to think of them as modules. But just because people just borrow this concept from like traditional machine learning, so they keep like the notion of experts.
I see. Although actually that can refer to very different things, right? Because modularity and using experts could be totally different, and they are orthogonal.
Yeah, exactly. So it's best way to think about this like a mixture of modules, but people just somehow call it mixture of experts. I think it's just because the people wrote the paper at the beginning, they call it mixture of experts.
Thank you.
Okay. Any other questions? Okay, cool. So now we want to understand how those experts evolve into like specialized APIs or specialized modules. Okay. So to understand, to do that, we first, of course, we need some data model. Okay, the mixture of expert model. We need our data to require a lot of different modules to solve. It cannot be a single model data, right? If it's a single model data, then probably the expert won't diverge. Okay, so what's that type of data that has multiple modules? Okay, so we are going to consider the data, which is called a mixture of regression type of data, okay, or a clusterable data. Okay, so what's this type of data? Well, we consider a data that has k types of clusters, okay, and on each cluster it requires a different classifier to perform the job. Okay, just think of our original example, like each data, our original natural language processing example, you should really think of each chunk of data requires something different to process. Okay, for example, there's some chunk of data you need a copying operation, some chunk of the data you need additional multiplication operation. Okay, so we summarize or we consider a simplified version of those data, which is called a mixture of classification type of data. Okay, so those data has k clusters, and each cluster requires you to apply a different function on it. Okay, so each data belongs to one cluster, or some chunk of the data belongs to one cluster, and that chunk requires you to apply a different, and each chunk requires you to apply a different function on it. Okay, so an illustration of the data is like this. Okay, so we consider this type of data. So we have CFAR10 rotate data. Okay, so it's just generated from CFAR10, but instead of classifying the original label of CFAR10, we are actually going to do a binary classification that try to identify whether the picture is rotated or not. Okay, so why is this a mixture of classification type of data? Because you could think of each type of image, like whether it's a truck or it's a car or it's a fork, as one particular cluster. And you need to apply different principles in order to detect whether this image is rotated or not. Okay, for example, if it's a truck, then you may see some non-vertical edge, then it's rotated. If you see vertical edge or horizontal edge, okay, vertical edge or horizontal edge, then it's not rotated. But if your data is an airplane, okay, then for a standard airplane, if you see vertical edge or horizontal edge, it's not really saying that the airplane is rotated or not, because a standard airplane has both vertical, horizontal edge, and it also has non-vertical or horizontal edge. Okay, so you really need to first understand what is this image and then apply different criteria in order to decide whether the image is rotated or not. Okay, so ideally for a mixture of expert model, we want each expert to specialize on detecting one particular type of image is rotated or not. Okay, so we want, first of all, each expert, for example, expert 1 specialize on detecting whether a truck is rotated, and expert 2 is specialized on detecting whether maybe a deer is rotated. Expert 3 is specialized on detecting whether a cat is rotated or not. Okay, so those are specialized experts. Okay, and we do see that in this type of data set, mixture of expert model has a significant advantage compared to standard models. Okay, just on standard CVAR10 data, mixture of expert is actually useless because the CVAR10 data does not have like prescribed, very well-defined cluster structure. Okay, I mean, it is clustered, but the cluster, you don't really need to apply different function on each cluster. The cluster itself is actually the label of CVAR10. Well, for CVAR10 rotate, the cluster itself, which is the class of the image, is not really the label. Okay, you really need the expert to be specialized on each cluster, on each class, and then the expert decide whether the image is rotated or not. Okay, and the mixture of expert model really shines compared to the single model in this type of clusterable data. Okay, any questions?
So can you hear me? Sorry. And when you're speaking of rotation over here, what kind of rotation is there? Is it any rotation at all, or are you choosing a specific rotation?
We are rotating between 10 to 30 degrees. So it's a random rotation between 10 to 30 degrees, and you need to decide whether it's rotated or not.
So there's only one common expert to decide whether it's rotated or not. You're not splitting.
No, so we use 10 experts in the mixture of expert model. So each expert is going to specialize on detecting one type of image is rotated or not. I mean, that's our hope, right? For example, expert 1 will detect whether the truck is rotated or not. Expert 2 will detect whether a car is rotated or not. But of course, you need to know, I mean, you need to first understand what is a given image, whether it's a car or a truck, and then you just call those specialized experts once you understand what is a given image.
So have you found if the experts end up learning different rotations rather than different classes?
The experts are actually learning different classes, but it's not really like very well separated. So it's mixing some classes together, but we do see some cluster structure that, for example, there are experts that specialize on sheep, and there are experts that specialize on truck, but the experts that specialize on truck is also specialized on car, maybe because these two classes are too similar. So we have some table showing like what's each expert specialized on in our paper. So we do see something that we expect, which is the expert actually specialize on some particular type of image.
Thank you.
Okay, any other questions? And also the MOE really shines compared to single model here. Okay, and on CVAR10, MOE is completely useless. So this is a kind of a justification of MOE is only useful if your data is like clusterable and it's multi-module. Okay, and also there are some other justifications. For example, this type of data, this is multilingual prediction data. Okay, so it's a multilingual prediction. It has French and Russian and English, and you want to predict the sentences happy or is sad. Okay, multilingual sentimental prediction data. And here, mixture of expert model is also doing better than a single model. And we can see that those experts are really, really specialized on each language. Okay, so expert 1 is only going to do French, and expert 3 is also doing French, and expert 4 is doing English, and expert 3 is doing Russian. Okay, so we kind of really specialize on each particular language. Any questions? Okay, so cool. So now we know that mixture of expert model is working. Okay. And the question is, how are they working? Okay. How can the expert learn to be specialized? And how can the expert learn to specialize, and how would the router knows which data to assign to each expert? Okay, they're all just done by gradient descent, and we want to understand what the gradient descent is actually doing here. Okay. So now to understand this, I'm going to skip this slide. So we consider the most basic version of mixture of classification type of data, or multimodal, multi-module type of data, which is called mixture of linear classification. Okay. So what's mixture of linear classification? Well, mixture of linear classification is just a simple task where there are k clusters, and on each cluster, the data is really linearly separable. Okay. And our hope is that the experts are going to learn this particular linear function on each cluster, and then the router just pick which expert to use. Okay. So pictorially, this is a mixture of linear regression, mixture of linear classification data. We can see that here is one cluster that is linear separable, and there is another cluster that is linear separable, and another one which is linear separable, another one linear separable, another one linear separable. So there are like 1, 2, 3, 4, 5 clusters. Okay, and in each cluster you need to apply different linear function. Okay, and ideally, hopefully, we want to see that on this type of data set, the expert actually becomes a particular linear function, okay, that separates each on particular cluster, and then the router just assigns all those data to that corresponding expert. Okay, and is that really the case in practice? Okay, so if we just train an MOE model on this very, very simple data, its experts are going to specialize on each cluster, and its router are going to succeed to route to the data to the corresponding expert. Okay. Okay, cool. So here we consider a single expert as just a one hidden layer ReLU network, one hidden layer network with some nonlinear activation. In our work, we compare two types of activation. The first one is linear, second one is a nonlinear activation. Okay, so each expert here is just a one hidden layer neural network. Okay, and ideally we want this neural network to just learn kind of a linear separator. Okay, which means that this activation could just be linear, because we just want the expert to learn a linear separator here. So this activation could just be linear. Okay. So of course, even with linear activation, I mean, the good expert definitely exists, because the router can just identify according to those clusters. It's linear. I mean, those clusters are linear separable. And after that, the expert just need to learn a linear function. Okay. Any questions? Okay, now we are going to do the experiment. Okay, we are going to apply a mixture of expert on this extremely simple data, and we are going to see what it does. Okay, so what is a mixture of expert model? Well, mathematically speaking, a mixture of expert model look like this. Okay, so the summation of mixture of expert model is like this. Okay, so sum over this weighting thing times Fm of xw. W is the parameter of each expert. Okay, so Fm is like the m's expert, and you just sum over m, that are all the experts. Okay. So here, theta is a parameter of the gating network, so it will decide this part, which is kind of like what expert you want to route to. And W is a parameter of the expert, which is this part. Okay. And we use a linear gating network. So the gating network is just a linear function. Okay, so the gating network is just a linear function of the input. And then this routing probability here is going to be like a softmax. Okay. And the expert model, as we said, is just a one hidden layer neural network. And the routing P, and also there is this T of X, which is deciding which expert would the router select. Okay, so the T of X, we are going to use the so-called top one routing. So that router will only select the expert that has a maximum probability, okay, or maximum probability maximum probability in terms of the output of the router. Okay, so basically this is a router network. Okay, the router network, the output is in dimension m, so there are m experts. Okay, and the expert with the highest, I mean the or the index with like the highest value will be the expert that we select. Okay, and more importantly, after we select the expert, we actually multiply the output of the expert by this value, okay, which is the actual probability of this expert, okay, or actual probability of this router's output. Okay, so in this way, we actually have some gradient. Okay, if we only do like top one routing, then then the router part will not have gradient because the max function here, the argmax is not a differentiable function. So people actually, after picking the argmax, they actually also multiply the output of the expert here by the probability here. Okay, so the probability part will have gradient. Okay, any questions of the architecture? Okay, cool. So this MOE layer is very, very standard. This is the actual layer that people use in practice. Okay, so you use the argmax of the router to select the expert, and after that you multiply that expert by the router probability. Okay. Okay, cool. So now we apply this MOE model on our particular data. Okay. So the first thing we are going to look at is using a linear expert, because we know that the model is, the data is a mixture of linear classification data. So linear experts is definitely enough to separate the data and to get a good result. Okay. But the point is, if you use linear expert, the MOE actually is not going to work at all. Okay. So the mix, you can see the colors indicating like the router's assignment. Okay, all the blue points, all the kind of green points are the points that are assigned to one expert, and all the blue one are the points assigned to another expert, and all the red one are the points assigned to another expert. Okay, you can see that those experts are not specialized on each cluster at all, and they're just learning some arbitrary function. You see this expert learns both positive and negative part, but across a lot of different clusters. Okay, so it's kind of, this expert actually learns this blue expert actually learns some separation like this. Okay, and the green one learns some separation like this. So it's definitely not really specialized on each cluster, and the router is definitely not working. It's not really what we expect. So this linear mixture of expert is not really working. Okay, but on the other hand, if you switch to nonlinear expert, just to say the nonlinear thing is absolutely not necessary to separate the data. Okay, this activation is useless in terms of separating the data. But if you use a nonlinear expert, the training will actually work. And now you see this perfect picture. Okay, so each expert do specialize on one cluster, and they are really just learning this linear separator. Okay, although it's actually using a cubic function activation to approximate that linear part. Okay, any questions? So the takeaway message is mixture of expert does work in this setting, but it only works if you use a nonlinear neural network as your expert. Okay, if you use a linear layer as your expert, it's not going to work at all. Okay, so this kind of justifies that in practice, you have to make sure that each expert is at least a one hidden layer network with nonlinear activation. Okay, If you use linear thing as your expert, it's not going to work at all, even in this mixture of linear regression data. Okay, this has nothing to do with representation. It's really just after training, the expert fails to specialize and the router fails to diverge. Okay,
how many experts did you have in this example?
Sorry, what?
How many experts did you have in this example?
This example are just 5 experts, I think, just 1 or actually 4 experts. So in this example, I think it's 1, 2, 3, 4. I think it just have 4 experts in this example, and we actually have 4 clusters in this example. Okay, and this is TSNE visualization, so it's not really look very linear, but those clusters are linear separate. Okay, does it answer your question?
Yes, thank you.
Yeah, so there are 4 clusters and we use 4 experts, and the mixture of linear thing, although it representationally has no problem, but if you train it, it doesn't diverge. Okay, on the other hand, the nonlinear experts is kind of the key to diverge. Okay, so now we pin down the point where that leads to the expert to diverge, which is this nonlinearity in this activation. Okay, so now we are in the next few, I think I'm having 10 minutes left, so I will discuss about how nonlinear is going to help and just a brief understanding of the entire learning process of MOE models just on this very particular example. Okay. Any questions?
Can I ask you number of
Yes.
experts? So for every problem, a problem could be solved by multiple experts in that field. So how do you come up with the number of experts?
Yeah, you can actually over-parameterize the number of experts. So maybe 2 experts will specialize on the same cluster. Okay. As we will see in the later slides, we will actually try 8 experts, and then there will be 2 experts that are specialized on the same cluster. But this MOE is still going to work.
Right.
Okay, any other questions?
Yeah, so I wanted to ask, like here you have this TSNE representation of your data, and here it more like looks like a 4 clusters, while the upper right cluster is not really like linearly separable in this like low dimensional projection, right? So what I wanted to ask is like if, for instance, if there was not this upper right cluster, do you think that just linear separation would work or no? Like that you wouldn't use?
No. I mean, this is TSNE separation. So
Yeah.
it actually makes a linear separable cluster non-linear separable. It's just an artifact of visualization. This cluster is still linear separable in the full dimension.
Oh, so it's a 1 cluster still. Okay.
Yeah, it is 1 cluster. Okay. So it is separable. This is actually a dimension 100 data, but we just use TSNE to project it to 2D. So TSNE is non-linear. So it actually make it look like it's non-linear separable, but it's actually linear separable.
Oh yeah, sorry. Thank you.
Yeah. Any other questions? Okay, cool. Now let's go to the mechanism of experts. Of course, we are going to consider experts that are randomly initialized. Okay, and we are consider gating networks that are initialized to 0. Okay. And we are going to train it with basically empirical loss minimization. Okay, and experts are top 1 routing with a noise perturbation, which is kind of standard in practice. Okay, so all of our settings are quite standardized. Those are the things that people use in practice. Okay, so we use a training algorithm, which is just some version of gradient descent, which is actually normalized version of gradient descent. Okay, and we can basically formally prove the result, but I mean the final the theorem statement is not that it's not that important. Okay, what we really want to understand is how this thing works. Okay, so basically we are going to show that the entire training process can be divided into the following stages. Okay, so there's the first stage, which is called exploration stage. Okay, during the first stage, the expert will diverge, but the router will actually be nearly on train. Okay, so it's not the router that are going to diverge first. It's not that the router is going to assign the correct cluster to the expert first. It's actually that the experts will diverge first. Okay, so this is very critical. The experts are actually going to diverge in our training. And after that, the router is going to learn. Okay, so there are two stages. The first one, exploration stage, which means in that stage, the experts are actually going to diverge and separate, and they're trying to explore. And after the expert diverge to a certain extent, the router actually catch up and just start to route the correct data to each expert. Okay, so this is the learning dynamics that we are going to show. Okay, any questions?
Yeah, hello. Do you hear me? I have one question.
Yes.
So it's not clear why they should diverge at all in this setup. So will you comment on that, or sorry if I missed something?
Yeah. I haven't said why would the expert diverge at all in this expert diverge stage, but our observation that is both empirical and theoretical, that we are going to say that the process look like this. So the experts, they first diverge and then the router catch up. It's not that the router diverge first and the expert catch up. The experts are actually the same, almost the same function at the beginning. So the router will not really train because it has no gradient if experts are all the same. And after expert diverge, then the router have big gradient and it starts to learn. So that's the process, but I haven't talked about why would the expert diverge yet. So I will talk about that later.
Okay, thank you.
Cool. Any other questions?
Oh, and just a quick reminder, we have kind of about 5 minutes for the talk. So
yeah,
can try to...
I'm going to just skip those things and just talk about the diverge of expert. Okay. So intuitively, let's skip those things. So intuitively, why would the expert diverge? Well, I'm just going to show it in one particular picture. The expert diverge really because of the non-convex landscape given by the non-linear activation. Just recall the linear experts are not going to work because linear expert, if you write down the laws with respect to experts, they're actually convex. And for convex setting, even if you start from different random initialization, those experts will actually collapse to the same point. Now, on the other hand, if you have a non-convex landscape, then those experts, even if they are pretty close at the beginning, they actually diverge. Okay, so in the particular case of that clusterable data and the cubic activation, we are actually going to we can actually prove that the expert diverge. But in general, in reality, intuitively the expert diverge really because it's a non-convex optimization problem. And the non-convexity is actually a bias here. And just thinking about the MOE model, probably you want the laws to be as non-convex as possible. Okay, those will actually help the experts to diverge to different regions. And when they start to different local minima, then the router is actually going to, route the data correctly to each expert depending on their specialization. Okay, so pictorially, pictorially just the expert look like this. Okay, sorry, I think I actually have a wrong picture here. Sorry about that. Maybe we'll skip this slide. Okay, but just to illustrate how would the router, just to illustrate kind of the expert diverge and the router entire framework, okay, we are going to use some measurement on how some measurement of the router. Okay, we are going to define the so-called entropy of the router. This is essentially just, you can think of the entropy of the router is very high if the router is uniform, and the entropy of the router is very low if the router actually routes the experts to the correct cluster. Okay, so we can see that at the beginning of the training, there's kind of the exploration stage where the router actually stays flat. Okay, so for nonlinear experts, there's like the beginning of the training. This is like the expert exploration stage where the router just stays flat. Just doing uniform routing is not trained at all. Okay, and when the expert learns, then the router starts to kind of very quickly decrease its entropy and just route the expert to the correct cluster. Okay. On the other hand, for for mixture of linear experts, there's really no exploration stage, okay, because the experts are not going to diverge, and the router just going to, start to train at the beginning and they just flatten. Okay. So this exploration stage where the expert actually diverge is kind of the critical key for the mixture of expert model to succeed. And this kind of also implies in practice, maybe we should train those experts first for several steps. And after that, we start to train router. Or we increase the router's learning rate towards the end of the training and decrease the expert's learning rate towards the end of the training. Okay, so maybe those are some practical potential when we train mixture of expert model. Okay, we want the expert to train fast at the beginning, but then we want the router to train fast at the end. Okay, so kind of that's basically a summarization of how mixture of expert works in this particular setting. And just for future directions, of course, we want to have more principled ways to make those experts diverge in mixture of expert model. And also, perhaps we want to revisit the idea that we don't want to train the experts. We just add artificial expert to the model. For example, can we add a compiler to the network, to the codex network that does coding? If I have compilers, then of course, it's going to do coding much better, but how do we actually insert the expert there? That's kind of a very important future question. Okay, but hopefully our theory just give you some idea of how those mixture of expert unit works and how do they diverge and how would the router, work together with the experts. Okay, so that's the end of my talk. Thank you everyone for listening. Any other questions?
Thank you very much, Yuanzhi, for sharing the insight. So wonderful. Now we have 2 minutes for questions. Maxime?
Yeah, so can you come back to the actual theoretical result you have? Because I somewhat missed it because there were many considerations, but the result itself?
This is the main result we have. So first of all, it's just saying the training works and then the testing works. Those are very standardized results. And we also say that basically each expert specializes on one particular cluster, okay? And then the router maps each example in that particular cluster to one of the experts or to the corresponding expert. So we divide the expert into, so there are K clusters, we can divide the expert into basically which clusters the expert specialize on, okay? And each experts are going to specialize on that particular cluster. Okay, basically these are the data on that cluster. And for each data on this cluster, the router will actually also route the data to the correct expert.
Okay, thank you. Just will be very curious. Do you have a preprint online somewhere to read that?
Yeah, the paper is online. It's called Understanding Mixture of Expert Model in Deep Learning.
Okay, thanks.
Yeah, any other questions?
Okay, let me see. I have a quick one. So suppose we have, suppose each expert is flexible enough, then in theory, you can even really learn the model for each mixture to really approximate the whole thing, the whole process. So in this case, I don't know why under what constraints actually we can benefit from in order to still learn different mixtures and kind of try to find a way, right, to see which one is the best in a particular scenario. I know you gave some understanding, right? You use the non-convex, basically say, oh, if the contract curve is not convex, then different experts may go to different local places. But there are kind of another way to see why the expert, we can really learn diverse experts in this case?
Yeah, I think the answer to your question is the experts in practice, they are very, very small. So they are just one hidden layer neural networks, exactly like our setting. So those experts are not really a gigantic network. This is a mixture of expert layer. So this is actually one layer in the neural network. So those experts are actually just one hidden layer neural network, and they cannot really learn all functions in the world. So they have to specialize. And also, I didn't mention here, but our theory also critically rely on this particular fact that each expert is not powerful enough to separate the data. So one expert can only achieve at most this many test accuracy. So those experts definitely need to work together in order to get like the best model.
Wonderful. So
So
saying that
basically,
you have to constrain the complexity of each expert. As a consequence,
yeah,
you have to allocate different kind of different problems, right, to different experts. Okay.
yeah. So if your expert is just a gigantic network, then probably it doesn't going to work well. So actually smaller experts are actually working much better. So people have tried, for example, using 3, 4, 5 layers networks as experts, and those are actually much worse compared to use one hidden layer network as an expert. So also people have tried, for example, using expert with 1,000 hidden units and 10 expert versus expert with 100 hidden units and 100 experts. And typically the smaller experts are actually going to be better. I guess that's also because they are potentially, the training potentially makes them more diverse.
So, Yunji, I have two questions. First, what happens if you make the whole thing hierarchical instead of just having one flat layer of experts?
Yeah, we did have some hierarchical expert experiment in our paper, but we didn't really know how to prove it in theory.
But empirically, what kind of does it perform better, or is it just the same?
At least for our current data set, we didn't really see a difference between hierarchical experts or single experts. But the point is, I think, let me go back to the experiment here. So for those CFAR rotate data, we found out that you just need to add one mixture of expert layer towards some middle of those networks. You can't really add it at the beginning because the router is just a linear function. It can't really classify the image correctly just based on the input. So you need to add a mixture of expert layer in some middle layer. But we found out that at least in our setting, just adding one layer is already good enough. Adding multiple mixture of expert layer is not that helpful. So potentially this could suggest that maybe we want to alter between mixture of expert layer and standard layer in practice. Maybe this could lead to better performance. I mean, I'm just hypothesizing, but definitely in our example, we only need one layer.
So have you tried this on the very simple XOR problem? Because an XOR really needs a plus shaped decision boundary. And this would be a classic proof of concept, right? That the expert shows which way the data are splitting. So on that problem, yeah.
Yeah, I think the XOR problem is almost the same as this mixture of linear classification problem, where you can think of, you have two clusters, and in one cluster you can apply a linear function, and another cluster where you can apply another linear function. So we did try XOR. We actually tried upgrade version of XOR, and all of them, the mixture of expert layer mixture of expert model are working, and it's actually, the dispatch is actually perfect, which means that all the experts are actually, all the experts just specialize on one part of the data. And the router just allocate to the expert perfectly.
Thank you.
So yeah, we tried more complicated setting. For example, we tried that the data just have one switch. So maybe the first several coordinate of the data tells me which function I need to apply. And then there are like 5 different functions I can apply to the remaining coordinate to decide the label. And then we train a mixture of expert layer on that type of model. And is actually working really well. And yeah, I mean, it's actually better than fully connected network or transformer in general.
Brilliant. So, and here's my second question. Have you tried, one of the issues we find with the standard classification models is that the decision boundaries they learn are not what you would expect. For example, on an XOR, if you train a standard MLP, it's going to learn 2 diagonal decision boundaries, which are odd, rather than the plus-shaped boundary. So now if I think of it in terms of adversarial instances or adversarial attacks, that's where the difference between the two really shows up. So
sorry, I can't hear you anymore.
Oh, sorry, I was interrupted. Diksha, you asked a question. Yuanzhi, did you give a response?
No, I didn't hear the second part of the question.
Okay, so the second part of the question is,
Yeah,
do you have, sorry.
Yeah, I heard about the adversarial training part, and
So okay,
hear.
So my connection is unstable. Have you tried any, do you have any investigation into whether this framework is more adversarially robust than standard frameworks?
I think on the CFAR rotate data, maybe it will be more adversarially robust. But on the CFAR 10 data, the mixture of expert model are not really like learning a better decision boundary compared to the single model. So maybe it's also learning a very weird decision boundary because there's no clear modality or no clear module in a CFAR 10 data. So perhaps mixture of expert model will improve adversarial robustness if you really have a mixture of classification type of data. So if your data has some very clear defined modality, okay, such as you want to, for example, you want to detect like the speed of some object, and you first need to detect like what's the resolution of the image, and after that you want to calculate what's the speed. And those type of like, you need to use different calculators on different like resolution. And maybe for those type of data, mixture of expert models are actually going to be more robust because it learns like a more natural decision boundary.
Thank you.
Okay, great. We are running out of time. So thank you very much, Yuanzhi, for the very good talk. And thanks to everyone for being with us. So thank you. That's the end of the talk. Yuanzhi.
Yeah, thank you everyone for coming.
If you are interested in the research, please just reach out to Yuanzhi. Yeah. Thank you.
Yeah.